In this lecture, we take a look at the dynamics of a simple harmonic oscillator. That is, we apply F equals ma to such a situation. This video, however, is specific to Honors Physics AB and AP Physics C. So let's apply F equals ma to the situation involving an oscillator, which is oscillating on a flat frictionless surface. So now we take a look at SHO dynamics. Okay, so here's a basic picture to get us started. We have a spring attached like so to a mass M. The spring has a constant K associated with it. Let's say that right here is the equilibrium position, and the oscillator, once again, is oscillating on a horizontal frictionless surface. Okay, recall that the displacement x from equilibrium is thought of as a positive number, and the spring force back towards the equilibrium position, described by Hooke's law, is then therefore a negative number. And now let's just go ahead and write F equals ma. When we do, the only force that matters here is the spring force. It's a horizontal surface, so the normal force and the weight cancel each other out, and there's no friction. So let's go ahead now and write F equals ma as the following. That is this expression here, like so. Okay, now this expression is not an algebraic expression. It's a differential equation instead, and the reason for that is because as x is continuously changing, the acceleration is continuously changing. So then therefore, how do we write this as a differential equation and then solve it? Well, first of all, recall that acceleration is the derivative of velocity with respect to time, and velocity is the derivative of position with respect to time. This then means that the acceleration is the second derivative of position with respect to time, and we write that then in the following manner. As I write this down, by the way, I'm going to take the mass m also and move it down to the denominator here on the other side of the expression. And now on the right-hand side of the expression, I'm going to write the acceleration as the second derivative of position with respect to time. And now what we have to do is we have to solve this differential equation. Here's what that means. What I have to do is I have to find an equation, x, that fits in here, and its second derivative with respect to time fits in here. That is on the right-hand side of the equation. If I find such an equation, then it is a solution to this differential equation. So let's go ahead and check the position equation from the lectures earlier on the kinematics of simple harmonic motion and see if in fact it is a solution to this differential equation. So basically, let's ask and answer the following question. Is our position as a function of time equation, this kinematics equation here, a solution to the differential equation? Notice, by the way, that I'm ignoring phase shifts at this point. A phase shift is just an unimportant mathematical detail. So is this equation a solution to the differential equation? Okay, well, here's how we answer this. What I do is I take, first of all, the position equation and I plug it into here. And then let's take its second derivative and plug it into here. Now recall, of course, from kinematics, so we already know what the second derivative of this expression is. It's just our acceleration equation, which remember is the following. This expression here. So let's now go ahead and plug the position here and the second derivative here, and then let's just see what happens. Okay, so first of all, on the left, I have negative k over m then times x equals then the second derivative on the right-hand side of the expression, like so. And then when I write this, notice that a bunch of things start to cancel out. So first of all, the negative signs cancel here and here. The amplitude cancels here and here. And the cosine omega t cancels here and here. And then here's what's left. Right here is an omega squared. And this then equals right over here on the other side of the expression, k over m. The last step is now just to take the square root of both sides. Like so. What we have done here is we have solved the differential equation. We have in fact shown that our position equation from earlier is a solution to this differential equation. However, the requirement for this to work, however, is that the angular frequency omega must depend upon the stiffness of the spring K, the spring constant K that is, and the mass M. Now, the first time that you see this process, it sort of looks like this expression just kind of pops out of nowhere, if you will. It's a product of the solution of the differential equation itself. So in just a little while, algebraically, I'll show you an alternate means of why this equation has to work the way it does. But before I do that process, let me demonstrate this equation to you. The easiest way for me to demonstrate the equation is not to think of it in terms of omega, the angular frequency, but instead think of it in terms of period. So let me go ahead and write this now in terms of period in the following way. Recall that period is 2 pi divided by omega. So take this new expression for omega and plug it into the denominator, and when you do, you end up with this expression here. So the period of the oscillation here, capital T, depends upon two quantities, the mass m and the spring constant K. So now let me go ahead and manipulate these variables here in a simple demonstration to show you how this expression works. Okay, I'm going to have to tilt my phone in order to do so. Like so. Okay, now let me go ahead and manipulate some variables. Let me first of all manipulate the mass m. So what I'm going to do is I'm going to use this loose spring here first, like so, and then just attach it like this. Then I'm going to start right here with a small mass. So if I have a small mass m, which is in the numerator of the expression for the period, this then means that the period is going to be small. The time necessary for one oscillation to occur is going to be a small number. This then means that the reciprocal, which is the frequency, is going to be a high number, a large number of oscillations per second. So let me go ahead and attach this carefully like so, and then set it into oscillation, and you can see here that the period is in fact quite short. Okay, now carefully, what I'm going to do is I'm going to use the same spring here like so, but now I'm going to increase the mass. So if I increase the mass, then I increase the period. The time necessary for one oscillation to occur is going to be a large number, therefore the frequency is going to be small. So let me go ahead and carefully attach this, like so. And now let me go ahead and set it into oscillation, like so. And you can see, in fact, that the period here is quite long. So if the period is long, in other words, the period is a large number, this then means that the frequency is a small number. So the larger the mass, the longer the period. Okay, now what I'm going to do is I'm going to demonstrate a manipulation of the spring constant K. In order for me to do this, I'm going to use this mass the entire time, but now let's think of it in terms of the spring constant. Obviously, this spring that I'm still using here has a low spring constant. So then therefore, if the spring constant is small, it's in the denominator of the expression, this then means that the period is large, like so. Once again, the frequency is a small number. Okay, now let me go ahead and remanipulate this. I'm going to use the same mass, but now instead I'm going to use this much stiffer spring. So this stiffer spring has a big spring constant associated with it. That's in the denominator of the expression. So if the spring constant is big, therefore the period is small. Time necessary for one oscillation to occur is going to be a small number. This then means that the frequency is high. Okay, let me go ahead and carefully attach this, like so. And now set it into oscillation, and you can see right here that in fact the period is quite short. So in other words, the stiffer the spring, the shorter the period, the higher the frequency. Okay, now let me switch to my main demonstration spring, like so, like this. And now take a look at the expression for the period once again. Notice that the expression for the period does not depend upon the amplitude. That's extremely important when it comes to timekeeping. I'll get to that in just a moment, but first of all, let me demonstrate it to you. So let me, for example, take this oscillator here and set it into a small amplitude oscillation, like so. As we'll see, the amount of energy that is here is a small number, but if with a stopwatch I measured the time necessary for one period to occur, it would be the same even at a different amplitude. So now let me go ahead and set this into a large amplitude oscillation like so. The energy here is more than it was before, but if I used a stopwatch to measure the time necessary for one oscillation to occur, it would be exactly the same number as it was earlier with a small amplitude oscillation like so. The period of the motion does not depend upon the amplitude. This is not just the case for a simple harmonic oscillator, but also for a realistic situation, what is called a damped harmonic oscillator. There's actually no such thing as a simple harmonic oscillator because as the spring here stretches and compresses, energy is lost as heat. That's completely unavoidable. So there are no such things as SHOs. Instead, we only have what are called DHOs, damped harmonic oscillators. So what that means is that over time, as energy is lost as heat, the amplitude here is decreasing as a function of time. We'll see that later on in this unit. However, the period of the motion still does not depend upon the amplitude, even when we take damping into account. So if I time how long it's going to take for one oscillation here, and then wait a few minutes for the amplitude to decrease appreciably, and then measure the period once again, it would be exactly the same number. This is extremely important because it allows us now to build a clock. All clocks, whether they be simple mechanical clocks or even atomic clocks, incorporate into their design an oscillation. And the reason for that is because the time necessary for one oscillation to occur does not depend upon the amplitude. So I could use this, for example, as a means of keeping track of time. The level of precision of my clock depends upon the period. So let's just say, for the sake of argument, that the period of the oscillation here is 1 second. Therefore, I could use this as a clock to keep track of time to an accuracy or a precision of within 1 second. Let's say that you have an electronic clock that you plug into an ordinary electrical socket. Alternating current has a frequency of 60 hertz associated with it. The period of that current is 1/60th of a second. Therefore, I could use that alternating current as a means of keeping track of time to a level of precision of 1/60th of a second. And that's exactly what we do with our spark timers and some of the spark timer labs that we have done over the course of the year. When we use those spark timers, recall that the time interval between successive dots that is made on the tape is 1/60th of a second. The reason for that is because the period of the alternating current is 1/60th of a second. Now, briefly, a few moments ago, I mentioned atomic clocks. What is oscillating in an atomic clock? It's actually not the atoms themselves. Instead, what's oscillating are the electrons from one energy level to another as they transition between those energy levels when they are excited by using laser beams. In the case of atomic clocks, the level of precision is within billionths of a second. And the reason for that is because the period of the oscillation itself is literally within billionths of a second. Because atomic clocks are so precise, we actually no longer base the second on the rotation of the Earth. Instead, we base the second on a specific electron transition that occurs within a specific isotope of some atom in an atomic clock. The atomic clock itself, the official clock of the United States, for example, is housed in Colorado Springs, Colorado at the National Bureau of Standards. At the National Bureau of Standards, there is an atomic clock there that is used as the official clock of the United States. And then around the world, other nations do the exact same thing, and periodically we sync the atomic clocks back and forth with each other such that everybody is basically using the same timekeeping system. Periodically, we have to correct for the wobbling of the Earth as it rotates. We've discovered that the Earth actually wobbles a little bit as it rotates because of the high precision of atomic clocks. So this has to be adjusted for periodically at like the end of the year, where like a fraction of a second is subtracted off the calendar for that reason. Okay, let me go ahead and retilt my phone back. Okay, like so. I'm also going to tilt it upwards. There we go, like so. Okay, so now let me go ahead and write down the following. Note that the period, capital T, does not depend upon the amplitude A. Therefore, an oscillator can be used as a timing element. When this discovery was made at the end of the 17th century, by the way, it led immediately to the construction of the first accurate mechanical clocks. So keeping track of time accurately didn't come until relatively late in history with this discovery about oscillations. So when this discovery was made, it led immediately to the construction first accurate clocks. Okay, now getting back to the mathematics of the SHO when we apply F equals MA to it. Okay, as I said a little while ago, the first time that you see me solve, for example, the differential equation, it sort of looks like this kind of pops out of nowhere. Okay, we've demonstrated it here pretty thoroughly, but let me give you an alternate means of visualizing why this expression has to work the way it does, and we could do so algebraically. We could do so algebraically in the context of conservation of energy. So let me go ahead and do a little bit of erasing here. Okay, so what we're going to do here is we're going to re-examine this expression for omega as the square root of k over m, and now in the context of conservation of energy. Okay, so let's take a look at 2 points in the oscillation. Okay, the first point in the oscillation is going to be the amplitude position. So let's say that right here is the equilibrium position, and right here is the amplitude position where x is equal to a. Recall at that instant, at the amplitude positions, that the speed v is equal to 0. So then therefore what that means is that at the amplitude positions, at that instant if you will, all of the energy of the oscillator is potential energy. So the total energy E, which is always kinetic plus potential, is going to equal 0 plus 1/2 k times x squared, where x is equal to the amplitude A. Therefore, the total energy E of the oscillator is 1/2 ka squared. Okay, now let's just take a look at an arbitrary point in the oscillation where the energy is a mixture, if you will, of kinetic energy and potential energy. So here's a simple diagram to illustrate. Like so. So let's say that right here, here's equilibrium. Now we're at some arbitrary position x, and the oscillator is either moving in this direction or in this direction like so with a speed v. So then therefore at that point in the oscillation, all of the energy is a mixture of kinetic and potential energy. So energy equals kinetic plus potential. It's 1/2 mv squared plus 1/2 kx squared. Okay, now because the energy is conserved, this quantity here has to equal this quantity here. So let's see if it does. Here's how I'm going to go about doing so. Let's take this expression here, 1/2 mv squared plus 1/2 kx squared, and plug into the expression the following. We already know, for example, what position as a function of time is and velocity as a function of time is. Let's go ahead and take those kinematics equations and plug them into this expression here. Now recall from kinematics, of course, that position as a function of time is the following. And then velocity as a function of time, which is the first derivative of position with respect to time, is equal to the following. Let's go ahead and take these expressions here and plug them into here, and let's just see what happens. Okay, so first of all, 1/2 mv squared. So 1/2 m times this quantity here squared. So the negative sign squares out, and then I have omega squared, a squared, sine squared, omega t. And then I have my next term, so plus 1/2 kx squared, like so. So now let's go ahead and plug into that then, the value of x. Let me just erase this and just plug it in. Let's go ahead and plug in the value of x, which is this guy here, so squared, a squared cosine squared omega t, like so. Do you see there the beginnings of a trig identity, specifically sine squared plus cosine squared, which is equal to 1? Can I use that trig identity here yet, however? Not quite. And the reason for that is because these coefficients here is not quite the same thing as these coefficients here. But let's plug into here the following. Omega is the square root of k over m. Let's go ahead and plug that into this expression here, and then let's just see what happens. So then therefore this quantity here is now equal to the following. 1/2 m times omega squared, so square this, like so, times a squared sine squared omega t. And then the other term remains the same. Like so. And now notice in the first term that the mass m cancels here and here. And now I have a 1/2 Ka squared here as a coefficient and a 1/2 Ka squared here as a coefficient. Let's factor it out. Like so, and there in the parentheses is our trig identity, which is equal to 1, and then therefore the total energy is in fact 1/2 Ka squared. Because the energy of the oscillator is conserved, this quantity here has to equal this quantity here. That's only possible if omega, the angular frequency, is equal to the square root of K over M. So there are two ways to look at this new term, omega being equal to the square root of K over M. Number one, it essentially is a product, if you will, of solving the differential equation F equals ma, but it also has to work the way it does from conservation of energy, and we could show that here as I've done algebraically. Okay, let me conclude this video here.